Welcome to this video lecture on the subject transmission lines and antennas. So in this lecture we are going to discuss about TM waves in rectangular waveguides. So first of all we can see this picture where can you relate the figures in this diagram. The first one is the rectangular waveguide, so which is a hollow metal tube, and second diagram is the parabolic dish antenna. So these pictures shows the waveguide antenna and also dish antenna, which are particularly used for very high frequency applications. So what is a waveguide? A waveguide is a special form of transmission line consisting of a hollow metal tube. So the tube wall provides the distributed inductance, while the empty space between the tube provides the distributed capacitance. So the waveguides are practical only for signals of extremely high frequency, where the wavelength approaches the cross-sectional dimensions of the waveguide. So it is only for extremely high frequency. Below such frequencies, waveguides are useless as electrical transmission lines. Next we can see the types of waveguides: rectangular waveguides and circular waveguides. So rectangular waveguides are the most preferred one, and frequency difference between consecutive modes are smaller. And circular waveguides are less preferable because the polarization is not maintained with circular symmetry. So we can analyze the rectangular waveguides. So here the rectangular waveguide of width A and the breadth B is shown in this diagram. So an electromagnetic wave is assumed to propagate in the Z direction as given in this picture. So for analyzing the rectangular waveguide, we use boundary conditions. So Ex and Ez is 0 at y equal to 0 and y equal to b. This is the first boundary condition. And Ey and Ez component are 0 at x equal to 0 and x equal to a. So this is the second boundary condition. And we are going to apply the Maxwell's equation and wave equation for the rectangular waveguide. So here the E is a component of the transversal electric wave in the rectangular waveguide is E is equal to 0. And Maxwell's equation and wave equation are applied here. Del squared E plus omega squared mu epsilon E equal to 0, and del squared H plus omega squared mu epsilon H equal to 0. And we are going to solve this del cross E equation, where curl of electric field equal to minus mu dou H by dou T. So by applying this we get dou Ez by dou y minus dou Ey by dou Ez equal to minus mu into dou Hx by dou T. So from this J beta Ez Ey equal to minus J omega mu into Hx. So similarly other two equations are solved. And from del cross H equal to J omega epsilon E, we get J omega epsilon E equal to del cross E is the curl of magnetic field. So the curl formula is applied here. So from this we can solve the dou Hz by dou y plus J beta Ez Hy equal to J omega epsilon E Z. Similarly other two equations are solved. So this is an activity. So for analyzing the TM waves in the rectangular waveguide, so TM means the magnetic field component is entirely transverse to the direction of propagation. So H is equal to 0. So the component of magnetic field along the Z direction is 0. So that Hx and Ey is automatically become 0. So the other components Ez, Ex and Hy will have the value. So we know that Hy equal to C3 sin Hx plus C4 cos Hx into e power minus gamma Z. Z is the direction of wave propagation. So the boundary condition cannot be applied directly here to evaluate C3 and C4. So because the tangential component of Hy is not equal to 0 at the surface of the perfect conductors. So for this we are calculating the Ez value by using Hy component, and applying the boundary condition C3 becomes 0 and Ez is given in this equation, and applying boundary condition 2 we get Ez, and also we substitute H equal to m pi by a. So we get Ez equal to minus m pi by a c4 divided by j omega epsilon sin m pi by a into x e power minus gamma z. So we can get other values by substituting this Ez value. First one Hy is calculated. So similarly other fields are obtained. So by substitute gamma equal to j beta for wave propagation, so we get Ez, Hy and Ex component. So these three components are the equations of fields of TM waves between the parallel planes. So these are the assessment questions. The wave in which the component of electric field is absent in the direction of wave propagation, so it is known as transverse electric, and the wave in which the component of magnetic field is absent in the direction of propagation is known as transverse magnetic. Thank you for listening this lecture.